That was embarrassing. I was trying to talk to you guys, and I didn't realize that I hadn't clicked it, apparently. That makes very little sense. Okay, let's explain. So for the notes today, we're going over the area problem. So what happened was I thought I was talking to you guys, and in reality, it wasn't streaming for some reason. So, um, okay, the first gap was the geometric series, and the geometric series is written as the sum of I equals 1 to infinity of a sub 1 times r to the I minus 1. So this is the formula we have from chapter 9. Okay, so this is a chapter 9 formula right here. So this is from chapter 9, we have this. This is an infinite geometric series. Okay, this is crucial information right here. Because the area problem is going to be a geometric series. I know, guys, it's kind of hilarious. I clicked stream, then it didn't load, then I thought I was loaded, and then that was like 5-10 minutes. So, great job there. So you guys can just write down these two blanks. So this infinite geometric series is the same thing as this. If you notice something, that connects geometric series with limit notation. So these two ideas are connected by this idea right here of a product. So we have our same answer, a1 over 1 minus r. Okay. So these are some properties right here, and you can copy them down as you go. This is the constant property. That is, if you have a sum of a property of a constant as I goes to n, it will just be c times n. So the n up here is infinity. Then we're going to have a oh no, it doesn't work. That's useless. Okay. I could do it a different way, but okay. So this is if we have some I in a number I at equals to n, you just replace it with n and times n plus 1. If I is squared, then you replace it with this formula over here. If I is cubed, where was that? Then instead we have n squared times n plus 1 squared over, and this is going to be over 4. Now, is there a reason behind this? Yes. In fact, you can deduce it through doing the math. But again, guys, these are kind of our foundations. Okay. So, what about if you have some subtraction going on? Sorry. What if you have a sub I plus or minus a b sub I? So, what if we had this? Then what's going to happen is it's essentially going to be that you can split it up. You can split up the sum if there is an addition or subtraction. So we're going to get both of them. So you're going to get this from I to 1 to n of a sub I. So that's going to plus or minus the sum of I equals 1 to n of Okay, so this is also the question about what about multiplication. So we have some k times a sub I. What's that going to mean? Okay. What that means actually is you can take the k and stick it outside the sum. Why is that useful? Well, if it's a gonna lose power. Guys, I'm gonna lose internet in just a second. It's gonna be some power. We're gonna do a some power. Okay, this is only when k is a constant. Okay, so these are our basic rules. Now we have some problems here where we can just kind of plug it in. So an example here is that this one is our I, so we're going to apply our rule right here. So it goes to 200, so U equals, and you do 200 times 201 times 201 divided by 2. And that's just going to equal, see, 100 times, so that's going to be 200, 1, 0, 0. Okay, so essentially we just plugged in this side right here. Okay, this one we're actually going to solve by splitting it apart. And what I mean by that is we're going to start with this. Start with the original equation. Actually, do we have space to? Let's subtract some space. Okay. So first thing is we're going to move this 1 over n to the outside because n for our purpose is a constant. Okay. Then we're going to have I equals 1 to n of I plus 2. Okay, and in that, the I and the plus 2 can be separated. So we're going to get 1 over n, and then in parentheses, we're going to choose the sum over here. Let's just choose this one, this, and this. So we're going to get the I, and it's going to be, and it's going to be plus, so it should be 2. Okay, and we obviously have our bracket. Okay, and then inside we can actually solve these two. So I, that's going to give us a specific formula, and this 2 is going to give us this formula right here, C times n. So we're going to get, keeping it on the outside, 1 over n, and then we're going to get in parentheses n times n plus 2 divided by 2 and plus 2n. So how do we solve this? Well, we need the same denominator. So this does not have a denominator, so we're going to get it the same denominator. That's going to give us 1 over n, still on the outside. So n squared plus 2n plus 4n. That's all going to be over, that's all going to be over 2. And then, so solving that out, we can factor n off the top. So I'm just going to do that. We get n times n plus 6 divided by 2n. And solving that, we get n, so n plus 6, n plus 6 divided by, plus 6 divided by 2. And that would be our answer. Sorry. I made a mistake here. Oh, this should be plus 1. That makes so much more sense. And then this is plus 1. So this is plus 5. So this is plus 5. Okay. It was just this plus 1 right here. So, again, you break it apart. So our first step, this. Then you can just plug in this n, right? N is 10, so you have 15 over 2. N is 100, so 105 over 2. N is 1,000, so 1,005 over 2. And N is 10,000, 10,005 over 2. Okay. Now, this would be growing exponentially. So, wait, did I miss something? Did I? Oh, that makes sense. Oh, n squared. So this would be n squared. This makes so much sense. So much sense. Okay. Sorry. I forgot that this n squared over here. Wait. Okay. Sorry. Okay. Upside. So we're evaluating these two sums, right? This one and then this one over here. I wrote something incorrect, so I'm kind of correcting it as I go. Okay. So this is 2. Okay. Okay. So this one right here, we're trying to find. We're trying to solve. Let's zoom in a little bit. Why is it? Okay. So we're trying to solve this one right here. Okay. And it kind of gives us the pattern of what's going on up here. We're just adding each time as we go up. So then we plug this in. And we're going to follow these properties that we've gotten before up here to solve it. Okay, so we're going to probably use this one, and this one. These are our properties. Okay, these 3 properties make it possible to solve this right here. Okay, here, I'll show the work on paper, since that's actually easier usually than doing it on a computer. Because on a computer, I just do it in my head. So, let's transition real quick to board and marker. Okay. So we're dealing with sums, okay? And sums are going to be either growing continuously or decreasing. Okay? And we're going to try to solve this one. Now, there's some properties here. N is a constant, okay? So we need to know that n equals a constant. Sorry, constant's not with a K. Constant. Okay? So we can actually divide it out based on one of our rules. So our rule tells us that we have n on top, 1 n squared. So we can factor off that. So we get I plus 2. Okay? Now, another rule we have is that 2 things added together can be separated into 2 different sums. And the reason why we want to do that is it makes it easier for us to solve this. So we solve this with I by itself, and then, sorry. Okay, now we separated them because we can figure out this one. N squared, oh sorry, that was just me writing it incorrectly. So it should be an n squared. Okay, that was a mistake. Okay, that n squared was supposed to be the original. Technically, I had solved it for the other way, but I digress. Okay, so then this this I, we would solve it. So it'd be there's our formula, n times n plus 1 divided by 2, and then 2 would be 2n. Okay, and then this is actually just going to be straight up multiplication division. And if you do it right, you're going to end up with n plus 5 over 2n. Okay? Now, if you're like, how do I do that with this math right here? What I would just suggest, get the same denominator, and then work it out and try to factor off and simplify. Okay? Okay. So, let's take some practice problems from the book. Okay? Sorry, gotta erase this real quick. Okay, let's erase. Okay. So, practice problem number 1. We have a sum to the 60 of I equals 1 of 7. What this means is we're multiplying 7 60 times. 7 times 60 is 420. So that would be our answer right there, 420. Okay. The sum is I equals 1 over 3n cubed, 1 plus I squared. Okay. Now, this one, again, this right here is just, this is the last section for the test. This right here is just a constant, because n is just going to be a number. So we can actually factor it off. So we get 3n cubed, I equals 1, n of 1 plus I squared. Now, these two are two separate things that we're going to need to separate. They're two separate ideas. Okay, the first idea is, so we get, is going to be the sum as I goes from 1 to n of 1 plus the sum as I goes from 1 to n of I squared. Okay, sorry. What is the sum of this? Well, the sum of 1 will be n. Okay. We'll have 3 over n cubed times n plus, and then this is actually going to be n times n plus 1 times 2n plus 1 all over 6. Okay, if you multiply this out first, if you multiply this out first, you're going to get the idea. 3 over n cubed, you're going to get n over 6, so we have the same base, plus n cubed, 2n cubed, 2n cubed, plus 3n squared, plus n over 6. Okay, combine like terms, and then bring in the n cubed. You're going to get, so you're going to get 2n cubed plus 3 squared plus 2n. If I factor off an n here, this would just be n on the outside, n squared, and n to the 1 over 6, that's 3n, 6n cubed. Okay, so I just brought this in and combined like terms. So in this fact, you can cancel. This 1, this is 2n squared. So our answer is 2n squared plus 3n plus 2 over 2n squared. And that would be our final answer. Okay, sorry about that. So that's our formula. Okay, that would be the process of finding the sum. Now it does take some time, but the reason behind why we do this is so that we can figure out area. It's actually just, it's okay. Okay. Again, this is going to follow the same pattern. You're first going to, this is just going to do the exact same thing. So first, you're going to multiply this out, get the same denominator, factor it off, and then solve it. Okay. Sorry, you cannot see that. Okay. So this problem right here, example number 3, we're not going to really do much more on, but this essentially follows the exact same pattern. First, you're going to square stuff, and then you're going to get the same denominator. You're going to factor it off and put it up in the front, and then solve the inside, bring it back in, and you'll be done. Okay, now, area problem. Okay, now when you did math in geometry, in algebra 1, in algebra 2, we kind of, not lied to you, but we oversimplified math. And what I mean by that is there's more to it. So, the area problem. The area problem is this. You will have an area in calculus of a figure like this. Now, this is probably going to be one of the simpler things. Say you have an area of under this curve. They'll ask you, what's the area of this shaded region? And if you ever plan on taking SAT math, the one with calculus, this is a question they would definitely ask. They would ask you, what's the area right here? And you don't have a good way of doing that before calculus. It kind of, you can approximate, but you can't really solve it. Now there is an easy way in calculus to solve this. In fact, this is probably one of the most basic area questions, like the bottom. Then you go up from there. Okay, so we are going to follow area. It starts with approximating. So let's say we zoomed in, and here's our area. If we started to take squares, okay, and we took squares of equal width. Sorry, if it's not equal width. Took squares of equal width. We could approximate. This is pretty close, right? There's some gaps, but it's not terrible. But what if we kept shrinking the width so that we could put more and more squares in? So let's say instead of doing this, I took in half. Okay. And with half, I took half here, took half here, so then this would be right here. Okay, that gave us more, right, closer, right? And what we learned is that as our width gets smaller, as width approaches 0, our area is more accurate. Okay? As width approaches 0, our area gets more accurate. Okay, sorry I wrote it so small. But basically, as width approaches 0, area is getting more accurate. And there's actually a formula to this. But first, let's write the definitions. Yeah, we'll finish most of this. Okay. Let f be a function. Let f be continuous and non-negative. That's just for the sake of, you can do negative, but it's harder. Negative on the interval from A to B. Okay, so interval means our x values. We're looking at x values from A to B. The area A of the region bounded by the graph. That means contained, bounded by the graph of f. The x-axis and the vertical line. So the area contained by the x-axis, the graph of the function, and the vertical lines. What are the vertical lines? Well, the vertical lines are x equals a. So x equals a. So x equals a is our first one, and x equals b. So we're actually finding the area of a graph that is defined by this interval with these two lines, our x-axis and our graph. And it's given by this formula right here. It's gonna, sorry. Okay, hold on. I'm having some trouble with this, so we're gonna switch. Okay, sorry. Can't do that way. Okay, we're going to go to limit as, so our area A is going to equal the limit as n approaches infinity. Okay, as n approaches infinity of the sum I equals 1 until n of f of a plus b minus a I over n times b minus a over. Okay, so this is going to be our length. Okay, let's zoom in a little bit. Super zoom in. Okay, this right here, f of this is going to be our length. Let's do some shapes. So this right here, is going to be the length. Okay, that right there. Sorry, this whole thing. Okay, that whole thing. Now, this right here is going to be the width. Okay, that whole thing is going to be the width. So, if you notice something, this is going to approach infinity. This is going to approach 0, in a sense. Okay, as this approaches infinity and this approaches 0, we're going to not know what to do. But there is a clear, this is actually called, I believe this is a Riemann sum. So this is the Riemann sum of a function. Riemann sum, Riemann. Anyway, so this sum right here is crucial for mathematics. So this will give us boxes, infinite boxes right here. Infinite boxes that will give us the area of the function. And why is that important? Well, great question. It is important because a lot of how we understand the area of a room, the area of a country, is based on this very idea. They set n to some number, and then they solve, okay? So let's look at some stuff. Okay, find the area bounded by the function, okay? So we're going to look at this. I'm going to then move to show you, okay? I do have 5 more minutes, and this is our last problem. Okay? So, 5 more minutes, this is our last problem. Okay. So, we're going to start with, so we have the limit as n approaches infinity of the function I equals 1. That's a whole different problem. I equals 1 to n of, and this is f of, sorry, I'm just going to write out the formula, a plus b minus a I over n times b minus a over n. So they gave us that a equals 0 and b equals 1 and f of x equals x squared. Okay, so let's plug it in. We have the limit as n approaches infinity of, so we're going to plug in this into x squared, so we get a plus b minus a I over n squared plus b minus a over n. Okay, now for our purpose, we're going to ignore this limit. Sorry, there should be a sum here. Sum of I equals 0, I equals 1 to n. Okay. Okay. Now we're going to ignore this limit for a second and just deal with the summation. Okay. And here in the inside, I'm just going to kind of write it out. Okay. The a and the b. How do I do this? With the a and the b, we know, so we're going to plug them in. So we get the sum as I equals 1 to n of a is 0, so that cancels. B is 1, so we get I over n squared times 1 minus 0 over n. So we get the sum as n of I equals 1 to the I squared over n squared times 1 over n. Okay. So we're going to finish this up with, actually, I do want to continue, but I do have another thing to do. So I'm going to finish this question up. Okay. So, why do we have to, oh, okay. So then we get sum n of I equals 1. We're going to factor off the n cubed that we would get right here. So I squared, and then this equals 1 over n cubed. N I equals 1. So we get, after we do the sum, of I squared, we're going to get n times n plus 1 times 2n plus 1 all over 6. And then if we factor it off, we're going to get we're going to get 2n cubed plus 3n squared plus n over 6 n cubed. So we're just put it all together into one thing. Then, what if we took the limit of this? So we're going to come back to this limit. Limit as n approaches infinity of 2n cubed plus 3n squared plus n over 6n cubed. Well, this is the same thing we did before with the h, with the limit as it approaches infinity. So you see these two powers are the same. That would mean that we would get 2 over 6, which would be 1 over 3. So we just look at the coefficients and solve it. So then our area is actually 1/3. And as you do math, this will become clearer and clearer. Okay, so this is the limit right here. See this limit? Yeah, same power, canceled, 2 over 6. Coefficients becomes 1/3. Yeah, I know that's crazy, right? You're over here. You're like, there's tons of stuff. None of this is gonna make sense. Same power. Boom. We're back to we're at a coefficient. Okay, that's our goal oftentimes. Okay, so guys, I'm going to upload a video on the rest of this. There is what, 4 problems? Yeah, 4 problems. I'm going to explain them, and that problem, the area problem, so the way I'll explain it right now is area problem you wouldn't see until later in calculus. You don't see it at the beginning. At the beginning, you see limits. So the most crucial thing is the question, do you get how limits work? Do you get how left-hand limit and right-hand limit have to equal the same for that limit to exist? So the test is gonna really focus on the main points, okay? This is a good point. I mean, if you guys got this, and you got the tangent line problem, you know calculus, which is such a weird concept to say, that you actually know how calculus works, even if you would be like the slowest person in the room. Because derivatives are tangent line problems, and integrals are area problems. And they relate to each other. Do you need to memorize the formula? Now, that's a hard formula. I don't think it's reasonable to make you memorize it. This formula right here, I don't know off the top of my head. And I do know how to do it. So, let's just say you don't need to memorize this for life. But here's the difference, Dan. If you actually understood this problem right here, you would be so good at integration that it would be like, you could get a PhD, basically, how important this formula is. But anyway, I'm gonna upload a video explaining the other problems so you won't be super confused. And the homework will be due, let's say Tuesday. No. I'll just do Monday afternoon, but it'll be a shorter problem. If you have issue with Tuesday or Thursday for the test, please write in our pre-calculus, and I'm going to go on. So thank you guys so much for joining. I will see you guys, well, I won't see you guys again until next school year. Bye.